Greetings, fellow physicists, and welcome to our second topic in the area of circular motion, gravitational fields, and orbits. So to start off, let us define what exactly gravity is. Now, if you go back to our mechanics videos, in the forces one, you'll find a base definition of gravity, but the real gravitational definition comes from our buddy Newton in his universal law of gravitation. A very grand name. Now, the universal law of gravitation has a few key tenets. The first of which being that everything exerts an attractive force on every other thing. So everything in the universe attracts everything else to it to some degree. Second tenet is that that force is gravity. So that's gravity. It's the attractive force between all bodies. It's inherent. And the third one, written down in formula form, is that the force of attraction between two bodies is proportional, directly proportional, to the product of the masses of the two bodies, and inversely proportional to the square of the distance between them. And that's just a proportion, so you can't really do anything with it, but our buddy, the great physicist Cavendish, Henry Cavendish if you've heard of him, did an experiment and came up for us with a gravitational proportion, constant of proportionality, which we labeled G. So now we have the force between equals the gravitational constant times the product of the two masses over the distance between them squared. And the gravitational constant happens to equal 6.6742 times 10 to the negative 11th meters cubed per kilogram seconds squared. Now that's a weird unit. You might ask, what's the purpose of that? But that's because newtons are kilograms times meters over seconds squared. And so that extra kilogram on there gets rid of the extra kilogram that comes from these. And the extra 2 meters up here get rid of the extra 2 meters that come from here. And so it's a pretty simple topic there. So that is our formula that we use to determine the gravitational attraction between two objects, more specifically two spheres. Yes, this only applies to spheres. If you're not spherical, then Newton has no time for you. But fortunate enough for us, most of the planetary objects that we will be dealing with are spheres. So it's pretty easy. So first let us deal with the example of an apple, which I know isn't perfectly spherical, but it's spherical enough, right? Just got that divot in the top with a stem and a leaf, and the Earth. And so let's plug the stuff into this formula. We know that the mass of the Earth is 5.97 times 10 to the 24 kilograms. The mass of an apple, let's just suppose, is around 250 grams. And the distance between them while the apple is falling, well, let's not say the apple's falling. Let's say the apple's on the surface of the Earth, on the equator to be specific. And that distance from the center of the Earth, at center of mass, to the apple, in that case would be 6,378 kilometers. And so if we were to plug that into our equation with the 6.6742 times 10 to the negative 11 multiplied by 5.97 times 10 to the 24 kilograms, which in turn is multiplied by our 250 grams, which translates into 0.25 kilograms, over 6378000 meters squared, and we'd end up getting a value of about 2.43 newtons. That is the force of gravity in between those two objects. Now, what can we also calculate from that? We can calculate the acceleration of which that apple is accelerating towards Earth, because we know, according to Newton's second law, that force is mass times acceleration. And so, if we take the force here, the 2.43, divided by the mass of the apple, our 0.25 kilograms, we end up getting something around 9.79 meters per second squared. which you might notice is awfully close to 9.81 meters per second squared. But we just supposed the mass of the apples, so that's why it's not exact. But that is the acceleration due to gravity, or, as we would call it, the gravitational field on Earth. Now, what is the gravitational field, you ask? What is a gravitational field? Well, that's simply the field that gravity exerts, because gravity isn't like any of the forces we've studied before. Gravity is not a contact force. If you think of other forces like the normal force, for instance, it's a contact force between two objects. Friction, as a component of the normal force, it's caused by the normal force. It's also a contact force. Sliding, it's contact. If you think about tension, it's because of the contact between the sphere and the rope and whatever the rope is attached to. However, gravity, you could be hovering above the Earth all the way up here, but gravity is still acting on you. And that is why we have gravitational fields. We represent these gravitational fields using field lines, which actually point inward to represent where the object will go. And those gravitational field lines will grow longer the wider their influence, and thicker the stronger they are. That's the idea behind gravitational field lines, but how do we calculate the gravitational field? Well, it's a pretty simple concept. You take the force, you put it over the mass, and you have your field, which we represent with little g. Now you would notice that little g is also the same symbol for the gravitational acceleration on Earth. Well, that's because the gravitational field is the gravitational acceleration. Think about it. Unit for force, newtons. Unit for mass, kilograms. What is a newton? A newton is a kilogram times a meter per second squared over a kilogram. Cancel out the kilograms, you get meters per second squared, which is acceleration. That's the acceleration due to gravity. If we insert this, if we assume that the object falling is a sphere, we insert this using the Newton's universal law of gravitation, we can then determine that the gravitational field equals the gravitational constant multiplied by the mass of the larger object over the radius, or not radius, in this case the distance, I know it's kind of confusing, the distance between the two objects squared. Bam! That's your gravitational field. Now when we're close to Earth, and the curvature of the Earth is pretty much lost, we can assume that gravitational field is uniform, which is why we can use g as a constant when you're like throwing a ball really close to the Earth. And when you have an object floating between two objects that exert gravity on it, gravitational field lines are there because they're vectors. And you can therefore use them as vectors because the gravitational field strength is a vector, and you can add them up to end up getting a resultant of some kind. Now, the final topic we're going to cover here is the idea of orbits. Now, remember in our last video when I said centripetal force centripetal, can be caused by weight. And that is the case with the idea of Newton's universal law of gravitation, or in this case, Kepler's third law. Now, Kepler's third law is pretty simple. So we know that our centripetal force, the formula for that centripetal force, is going to end up equaling our mass times our angular velocity squared times our radius. And since we know that our weight in this case is our centripetal force, the force of gravity, then we can equate these two equations. And if we replace that angular velocity squared with something we know equals angular velocity, say 2 pi over the period, and then we balance it all out to solve for this particular, for t squared over r cubed, we'll end up getting, you rearrange it, right? You end up getting this lovely equation, which allows you to determine the orbital period and the distance between two objects of a sphere that rotates around another sphere. Bam, that is Kepler's third law. Now, of course, this doesn't perfectly apply. In fact, most planets' orbits are more of elliptical orbits, but we don't really need to know about that for the purposes of this physics course. And that'll be all for circular motion. Please join me next time for something that ties right into this: simple harmonic motion.